Welcome, everyone. Thank you for joining us today. The title of this panel is Fusion Energy Prospects. Here's a brief overview of what we will be discussing. Nuclear fusion has the potential to become a revolutionary new energy source, which would serve to be the foundation of a future sustainable energy grid. However, for this to become a reality, we must overcome many challenges, both technical and economical. Despite these obstacles, the past 12 months has seen more investment in fusion technology than ever before. So we want to cover what are some of the key advancements made in theory, computation, and materials over the last several years, which has spurred this new interest. What are the challenges that still must be overcome? And what is currently being researched both locally and internationally. Before I continue, I'd like to thank our hosts, the Madison Life Member Affinity Group, and the Madison PES IAS chapter. Again, I'd like to thank Charles Cowie for all the organization work he's done. We very much appreciate your help in making this event possible. Now, just a few things on how we're running this panel. The first 30 to 40 minutes will consist of moderated questions for the panelists. During this time, audience members feel free to use the chat to talk amongst yourselves. Then closer to the end of the hour, we will move on to audience questions. You can use the chat to ask a question. We'll be answering those first. But if you want, you can also use the raise hand feature and we'll eventually get to you and you can ask using your mic. Today's session is being recorded and it may be posted on the IEEE R4 YouTube channel at a future date. And at the end of the meeting, we'll be putting some sources in the chat if you want to do further reading on some of the topics discussed here. Now let's do some introductions. My name is Zander Keith. I graduated from UW-Madison in 2021 with degrees in computer engineering and computer science. I'm currently a research intern in the helically symmetric experiment, or HSX lab, and I'll be the moderator of this panel. And I'd like the panelists to introduce themselves, starting with Dionysi.
Yes, hello, my name is Dionysi Damaskopoulos. I am going into my second year in electrical engineering, a PhD program with the same program that Zander's in. I come to Madison from Colorado, actually. Prior to school, I worked as a deployment engineer of self-driving vehicles. So I would set them up around their route. They drive where they please. Previously, I completed my undergrads from Colorado School of Mines in electrical engineering, mechanical engineering, and I spent a little bit of time interning with Xcel Energy over in Colorado in the system protection engineering group. So, but today I want to focus my life into fusion. So I'm with this experiment, this project.
Excellent, thank you. How about Luquant next?
Sure. Hello, everyone. My name is Luquant Singh. I'm a PhD candidate in electrical engineering at UW-Madison. I work alongside Zander and Dionysi in the HSX experiment. My degree is focused on plasma physics and controlled fusion, which is why I'm here. And I did an undergrad and master's at UW in math and applied physics. My research at the device is focused on improving confinement in stellarators, which is what we all do here. It's a type of magnetic confinement device, and it's a candidate for a future nuclear power plant. And so, yeah.
And Kunal?
Hello, everyone. My name is Kunal. I'm going to, starting this fall, be a third year in the PhD program at UW-Madison in the physics department. My work is on the WHAM experiment, which stands for Wisconsin HTS Axisymmetric Mirror, which is a previously explored and then recently reinvigorated method of confining a plasma. And this is a new experiment to explore new breakthroughs in this field and test them experimentally.
Thank you. And last but not least, Dr. Ferry.
Hi, I'm Sara. I am a research scientist at the PSFC. I lead a lot of our fusion materials efforts, especially the Libra molten salt breeding experiment, a new vacuum vessel experiment, some work on high entropy alloys, a few others. I did my PhD in 2018. My main initial education before fusion was in fission materials. So sort of but because it's materials, you can kind of easily sort of go between subfields. So I started working full-time in fusion probably 2019-ish with the advent of a lot of the new work that we've been doing in the MIT department. So yeah, it's great.
Excellent. Thank you, panelists, for joining us tonight. Let's get into the questions. First, for Dr. Ferry, what is fusion and what does the fuel cycle look like?
Sure. That's a big, big question, right? So fusion is just the way that we'll probably be talking about it here is lighter elements when they fuse together, and that releases energy. It's an exothermic reaction. This is usually presented in contrast to fission of heavier elements, in which the radioactive elements, when they interact with a neutron, become unstable, split apart, and this releases energy. And in either case, we are talking in the context of fusion power about using that energy to usually create heat, which is then converted into electricity. So at the end of the day, everything is usually just a fancy way to boil water, is how we will talk about it in fission. It's not too different in fusion. That's sort of the high level view. The other panelists, I'm sure, can get more into the technical details if they want to of what fusion is and what the physics are. But the fuel cycle is, in the case of fusion, is going to be related to the choice of elements that you are using to create your fusion reaction. And the one that I'm familiar with, and the one that I expect we'll be talking about the most here, is between deuterium and tritium. And so these are light isotopes. Deuterium is relatively common, tritium is not. The reason why we are using them, despite certain drawbacks, such as the lack of or relative scarcity of tritium, it's not something that you can buy in large quantities for any type of money that makes economic sense, it is the easiest of the reactions, the fusion reactions that we can create like net power with to accomplish. And so I'm sure a lot of you on this panel, if you've looked into this field at all, know that it's quite difficult to make the fusion reaction happen in a way that we get more energy out than what we need to put in order to contain the plasma for extended periods of time. There are going to be, in the field, there are proponents of alternate fuels, like such as proton boron, because sometimes these let you get around certain difficulties, such as the need for tritium, the need to breed tritium. However, these reactions are much, much harder to happen efficiently. So from an engineering, so they make perfect sense from a physics perspective, but from an engineering perspective and trying to create economic fusion power, we already have major challenges just on easy mode, right? So that's sort of the thinking right now, or most commercial, we would expect that the first major tokamaks that would break even are going to be DT fueled. So when we talk about the fuel cycle, we're talking about both deuterium and tritium, but usually people will be focusing on tritium when they're talking about the fuel cycle because of the need for any fusion I want to say I say reactor. Some people get mad if I say the word reactor, but I'm going to just because it's simpler. So any fusion reactor, at least in the initial generations, is going to need to breed its own tritium. And there's going to be several aspects to how much tritium they need. This includes tritium for its own startup, the tritium that it needs as it continues through its operation, some amount of reserve tritium in the case of, temporary shutdowns or like maintenance on part of like the fuel cycle components that sort of extract and purify tritium, and importantly, tritium to start up new reactors. So these are all amounts that we can kind of tweak through engineering with regards to the startup inventory that is required. How much tritium you decide that you need in your reserves is something that comes down to more complex models of how your availability and your maintenance schemes. And it's challenging because I'm trying to think of how best to describe this. So we don't have a reactor to practice on, right? So a lot of our work right now is either very small scale experiments or relegated to modeling. And so we're trying to understand, how do we create very robust systems external to the tokamak and the magnets where the plasma is, to both breed the tritium and then to extract the tritium from whatever you're using to breed it and purify it and re-inject it into the fuel cycle. And it's quite a complex set of components, and they all are at relatively low technology development levels. So there's a lot of work to do in this regard. And recently, there's been a little bit more focus. I particularly recommend the 2021 paper on tritium fuel cycles by Mohammed Abdu, showing that if the current trajectory as defined by, say, the ITER demo program, it is going to be practically impossible to reach tritium self-sufficiency, which means that even if we get to, really stable, robust, break-even plasmas, burning plasmas, we are still going to have massive engineering issues on that end unless we start working on that in parallel with the plasma physics issues and the magnet issues that we tend to think of as the priority. So I'm sorry, that's very long-winded, Zander, but that's sort of the basis, I guess, of some of the stuff that we're working on here at MIT.
All right, well, thank you for that. Yeah, and thank you for touching on some of the deeper challenges that we're facing. Dionysi, could you expand on that a bit? Like, why is, I guess, taking a step back a little, why is fusion an energy source that worth investing in? Like, why are we putting so much time and effort into making fusion a reality?
Yeah, I think it might be wise to look at it from two approaches, right? One, we will have a very large growing demand for electricity, right? We could use more electronics as, other parts of the world start to demand more. There's a greater need for demand and power, and then there will be a need for decarbonizing or at least becoming maybe carbon neutral, right? And so fusion can help do both, right? You have a lot of renewables. Maybe some of you are power electronics engineers, that solar and wind are becoming helpful and they're quite useful, but they are not going to replace baseload power, right? We may need to be replacing our coal power plants. The idea of a fusion power plant should be able to replace that. I think people expect the kind of first generation fusion power plants to generate roughly the same amount of power as coal power plants. They're going to provide that steady baseload power. And they do this without producing greenhouse gases. There are, I guess, nuclear byproducts, maybe that'd be the right way to explain it, but it's nothing like fission reactors, nothing like today's nuclear reactors. They're not nearly as long-lived. I think they're on the order of decade, 100 years, Sara, something along those lines, the half-lives. So it's something that, at least within a few generations, we can understand, we can keep track of, and they'll cool off. So that's kind of why we want to start investing in that. Today, we still don't have that, right? But we are starting to see startups get involved in this too. A lot of investors want to get involved in that. You find that, I think last year, what was it? The private industry, which, at least among, I think maybe 4 private companies, they raised about as much funding as the national labs and the universities did. What would you say, in the past 10 years, was it? I mean, it's a really outrageous money that's going to just a few companies. So people see that this can be useful. They want to get involved in it. And we want to, go fast towards that goal. So, is there more that you think I want? Any more details there? Is that a good response?
Yeah, I think that's a good overview for now, yeah. And then for Luquant, how do we go about actually achieving fusion here on Earth?
Sure. So Sara mentioned tokamaks and several other aspects of magnetic confinement, but the basics of how we want to achieve fusion on Earth, at least for the people on this call, I'm not going to say these are the only ways to achieve fusion, but we would like to use magnetic confinement, which just refers to using magnetic fields to kind of guide plasma particles and hold a plasma in place. So the kind of key underlying physics that everyone has to know in this field is that plasmas are composed of charged particles, and then those charged particles interact with a magnetic field, and you can use a magnetic field that's kind of specifically tailored to guide your particles where you'd like them to go and confine them in some region of space. The reason we need to use magnets and we can't use something like a material wall is because for a plasma that we can actually shoot kind of these fusion fuels into, we need something on the order of 20 million degrees, maybe a little cooler, maybe a little hotter, but you're not going to find, at least as far as I know, a material that can withstand that type of heat load. Other examples of plasma confinement are like gravitational, the sun, which, you know, is kind of probably the most prominent plasma that we interact with, is confined by the gravity of the sun, but we can't possibly amass that, you know, insane amount of matter on Earth. So we have to use something else. There are several types of magnetic confinement schemes that have been come up with in the last 80 or so years. I work on one called a stellarator, and we've also got Tokamak Is represented in the crowd, as well as axisymmetric mirrors, which Kunal works on.
All right, thank you for that. Yeah, would we want to do a brief overview of each of those designs? We do have, like, as you mentioned, we have the good fortune to have 3 different magnetic confinement schemes here on the call. So maybe starting with the most prolific one, Dr. Ferry, could you give us a brief overview of what a tokamak is?
Yeah, sure. So tokamaks are what most people are going to think of first when they think of fusion. It tends to get the most coverage. It has probably the most representation in private industry at the moment. It's kind of the donut shape, where you are using a variety of very high powered magnets that surround your donut shape to confine a plasma current and sort of keep it at temperatures and confinement where you have a lot of fusion happening, and that is then throwing off like neutrons and heat and everything into your blanket. You breed your tritium, collect heat, et cetera, et cetera. And then there are multiple other options that the other panelists will describe that, while are less perhaps like developed on some levels, have like unique advantages that mean that, like, you know, as we move long term in the future, like we might actually start to see some of those designs actually become what becomes maybe the most prevalent. You know, fusion is still a relatively new field, right? So or rather not new, but relatively sparse with regards to like man hours on it if you compare it to other forms of power plants. So tokamaks are sort of considered the front runner right now, but that's by no means, like, first is not necessarily the end of the story when it comes to what fusion technologies might look like most 50 years from now.
And one of those designs that's seen a bit of a renaissance recently is the stellarator. Luquant, could you talk a bit about that?
Yeah, so stellarators in principle can be kind of similar to tokamaks. They're donut shaped, but they're kind of a messed up donut, little, not necessarily a donut you want to eat. And the main difference between stellarators and tokamaks is that the stellarator doesn't have any internally generated magnetic fields, so it doesn't have a significant plasma current. And this is, as Sara mentioned, a pretty unique advantage. There's a lot of kind of current-driven instabilities that arise in tokamaks due to this relatively large and crucial plasma current for them. And so stellarators in the past, you know, lacking this plasma current, didn't really have great confinement, but we'll talk about it a little bit on this call. Recent advancements in computation as well as theory, and then also demonstrations and experiments show that you can make stellarators with tokamak-like confinement, which is a relatively new aspect of stellarator research.
All right, thank you. And then Kunal, could you give us a brief overview of what a mirror is?
Yep. So a magnetic mirror is a very simple way to confine a plasma, and especially an axisymmetric mirror, which is the A part in WHAM. Your magnets are essentially your nice circular electromagnets. So it's the simplest type of electromagnet you can make. And the way it works is that you have a tube, and on the ends of the tube, you place 2 magnets. And so you have a magnetic field that gets really strong where you place your magnets and then gets weaker in the middle. And so the charged particles actually will just bounce back and forth between the 2 magnets, and they're confined that way. And that's why it's called a mirror, because your particles are just bouncing back and forth. Some of the advantages of this scheme are that it's a linear device. So in principle, you could make a magnetic mirror device that generates, you know, let's say 200 megawatts in a power plant. And if you need to go up, you can, in principle, just take that design, cut it, put more magnets in, and make the vessel just longer, and just generate, you know, an arbitrary amount of power, you know, within reason. Then, because it's linear, it gives you a lot of access on all sides, just physically, which allows you to explore different sort of heating schemes and allows you to put different diagnostics or more diagnostics, and there's an advantage there, as long as with the magnets just being a very, very simple design. Yep.
All right, thank you. You mentioned that on both ends of the mirror, there needs to be some really strong magnets, right? And there is a recent materials innovation that's helping you along with that. Yeah, could you give us a bit of information about what HTS is?
Yes. So the H part in WHAM, HTS, stands for higher temperature superconductor. And this is a recent advancement in material sciences where I think it's a ceramic based material, which people have figured out how to make these long tapes out of, essentially like a cassette tape. And you can wind it, again, much like a cassette tape, into a really strong magnet. And the reason that these magnets are strong is because so they're superconducting, but if you take a material that superconducts at, let's say, 70 Kelvin, and you cool it down to liquid helium temperatures, which is about 4 Kelvin, it can actually sustain a much, much higher field before it quenches, before it loses its superconductivity and becomes regular conducting. So that the advantage there is that it just allows you to get much higher fields, which is necessary for especially magnetic mirrors, but I think every device, Stellarator's Tokamaks, if you look at their scaling laws, all of them say that if you can get to higher field, it's only good.
All right, thank you. Let's go back to Luquant for a little bit. You touched on this a second ago with the computations that have allowed stellarators to become more optimized. Could you elaborate on that a bit more?
Yeah, sure. So before we do that, we probably want to talk a little bit about just general transport in magnetic confinement devices. Transport just refers to the movement of plasma particles and also their energy and their heat. In particular, we really would like to minimize the amount of transport out of these devices so that we keep our plasma in place and keep it a steady state device that is not is using as little energy as possible. And so I'm going to use a little visual aid here. Oh, Zander, I can't share my screen.
You should be able to now. Sorry about that.
No worries. I hope you can see that.
Yep, we can.
So I touched on this earlier. If you have charged plasma particles and then you have a magnetic field, you can control their trajectory. And this visual here kind of shows you that if you have a magnetic field and then a charged particle, it'll gyrate around this magnetic field line in this helical orbit. And so if you think about the net effect of that in an actual reactor, so I've got this here. This is a magnetic field kind of impinging a tokamak in this case, I guess it's circular, but impinging a plasma. And you can see I've shown two particle orbits here. You've got one that is confined, at least kind of in a classical diffusion frame. And then there's another particle out here that's near the wall. Based on the radius of this particle orbit, this red particle happened to not be confined because it was very near the edge of the device. And so this is kind of an example here in red of deleterious plasma transport. In this case, we don't necessarily care too much about this type of classical diffusion or classical transport because it's really only the particles that are kind of nearest the walls of the machine that really suffer. And in particular, as Kunal mentioned, if you increase the magnetic field here, you can pretty easily show that this radius will go down. And so by either increasing the magnetic field or by making the devices bigger, we can avoid, a significant amount of kind of classical transport. And then this is a very kind of idealistic magnetic field over here for magnetic confinement. A homogeneous kind of time-independent magnetic field is not really what we're working with in this field. So something a little bit more representative is shown here. And this is just a magnetic field that has some sort of gradient in it. And so this would be an example of neoclassical transport, which, as the name implies, is kind of transport beyond just this kind of classical helical particle motion that I just showed. And, I'm not really going to get into it here, but you can show that with the addition of this kind of inhomogeneity in the field, you'll get a net radial drift of these plasma particles outside of the plasma. And so now, whereas we were mostly concerned with kind of particles with either large trajectories or those very close to the edge of the device, now we can have particles that start kind of in arbitrary locations in our device. And then as time goes on, they'll make transits through our donut. And then over time, they'll kind of drift out of the device. And so that is the type of kind of consideration that HSX, the stellarator that I work on, has essentially tamed experimentally and computationally. So prior to innovations in the 80s, stellarators suffered from this kind of net radial transport outside of the devices because they don't have the type of symmetry that a tokamak has. And HSX is essentially the first stellarator to achieve a symmetric magnetic field, or at least kind of like mostly symmetric magnetic field that is able to kind of get rid of this net radial drift problem and make the confinement in a stellarator analogous to that in a tokamak. In particular, both of them are then dominated by turbulent transport, which is kind of like chaotic motion that's driven by microfluctuations in the plasma.
And that turbulent transport is still a fairly big problem that we're working on, right?
Very big problem.
Yeah. So, Dr. Ferry, you mentioned earlier that there's a component in a typical fusion reactor called a blanket. Not everyone might understand what that is. Could you give us a bit more of a in-depth explanation of what a blanket does?
Sure. Also, Zander, you're coming into the PSFC, right? So I have to insist that you call me Sara.
Okay.
It's lovely to hear it, but it's like no one calls me Dr. Ferry except like the bills that come to my house from MIT. So
All right.
the Sarah's, but so the blanket surrounds the plasma, and it usually will contain not primarily depending on your design, but a significant part of your blanket is dedicated to breeding material. And this breeding material will contain lithium. And when lithium interacts from the neutrons that come off the plasma, it will form tritium. And so in the DT reaction specifically, this creates 14 MeV neutrons. This is very fast compared to what we're used to in a fission reactor, where things are born fast at 2 MeV. So very, very fast. So slightly different neutronics. This is going to, just as a side note, this presents certain engineering difficulties because most of our nuclear materials experience comes from our experience with fission reactors. And so while there are quite a few similarities, the physics are quite different at these higher energy spectrums, and we have very limited experimental data to go on. So this is just another challenge to kind of bookmark in your minds for like when you're thinking about the challenges that fusion faces. So the fusion is, so to use the tokamak as an example, the blanket would surround sort of the donut where the plasma is. In the case of ARC, which is the reactor that I work the most closely, or tend to think about the most in terms of my work, this is simply a very large tank of FLI, which is a molten salt that contains lithium. And it's very, very simple. It's basically a big tank. Other designs, most of the ones that have been proposed, for example, the demo designs that are proposed to follow ITER, those are a little bit more complex mechanically. They also, depending on what I was just going to say, but they tend to be, they can use like solid lithium compounds or ceramics. Sometimes they'll use lead lithium, which is also a liquid, but they tend to have a much greater amount of structural material in the blanket. So things that are dedicated to cooling the blanket and extracting tritium, and where you're locating your breeding material, all in this contained in a solid structure. And a drawback of this is that the more volume that you dedicate to non-breeding material, the lower your tritium breeding ratio that you're able to achieve is going to be. And this is quite a difficult thing to elevate. So everything that we do on my end, when I'm looking at everything outside of the plasma, like I'm not a plasma physicist. To me, the plasma is a boundary condition that my teammates give me, and then I work from there. But you know, we can sort of make these models where like, okay, like this is like, we think that we can get this much tritium out of this much space, but when you move that into reality, the number is, you know, cut that down significantly. You've got losses everywhere, engineering problems that crop up. Tritium itself is quite a pain to work with. It's very small. It gets into lots of things. It goes where you don't want it to go. It combines with other things. So the blanket is there to breed the tritium. It's a very large component in a fusion reactor or a power plant. You don't see blankets on research tokamaks. So because they don't usually, even very few of them use DT as their fuel. And even those that do, you're doing it in pretty small amounts. So you do not need to breed your own tritium. There are other external sources that you can get the tritium from, but the tritium sources that exist right now, for example, like CANDU heavy water reactors, those are not going to be sufficient to sustain a fusion economy, which is why you see a fairly large subset of the fusion engineering community working specifically on optimizing blanket designs for different devices.
Thank you. Thank you for that overview of your current research. Could we also go to Kunal with your current research on WHAM? I remember you and Sara were talking a bit about WHAM acting as a neutron source, right? So what's the status on that?
Yes, so WHAM itself is a small scale plasma experiment, you know, on the order of $5 to $10 million, that aims to demonstrate the use of HTS magnets in a magnetic mirror. It aims to demonstrate how to demonstrate like stability of the plasma in an axisymmetric mirror, and also using like combining different heating schemes, like different ways to heat the plasma in a unique way to maximize the fusion reaction rate. So that those are the goals of WHAM. And then the next step device that we built based on the WHAM results, one of the paths that could take is a VNS, or a volumetric neutron source. And it kind of does what it says on the can. It's a plasma device that its job is to just generate a lot of neutrons, specifically neutrons that are useful for future power plants. So it's going to be generating these 14 MeV neutrons from DT reactions. And the goal of the VNS would be to act as a test bed for your tritium breeding materials, for your blanket materials, for your first wall materials, you know, just to make sure that you have all this neutron bombardment on whatever your plasma vessel is made out of. So you want to make sure that what you make it out of, you know, doesn't just crumble and collapse, you know, in a month or two. You want it to be solid and last a while. And so this is a platform that would allow you to test that sort of stuff. It also then acts as a facility for you to test your magnets. You know, do your HTS magnets do well in a neutron radiation heavy environment? How much shielding do you need? What type? How often does it need to be replaced? Yada, yada. And when the magnets do fail, what is their failure mode? Do they fail abruptly? Can you sort of predict how they're failing? You know, all that sort of stuff. And this is again where it being a magnetic mirror really helps, because it's a linear device. You have all this space around it to test a lot of materials, and the geometry of the plasma allows you to very quickly, you know, make changes on the machine. So it's very easy in a magnetic mirror to, you know, cut it in half, open it, change the inside material, and then close it up and start running again, which may be harder to do in other devices.
All right, thank you. Luquant, you talked earlier about how turbulence is kind of an issue faced by most current fusion reactor designs. How do we go about measuring turbulence? Because that's your research work, right?
That's right. That's a great question. So I'm actually going to show a picture of the HSX just for a visual here too. Oh, actually, that's a great slide. So in contrast to the previous examples of transport, turbulent transport looks a little more chaotic, because that's kind of what it is by definition. This is just an example showing kind of net transport out of the plasma due to essentially small fluctuations that are pushing blobs of plasma around. And this area of turbulent transport is notoriously difficult because we already kind of struggled to really understand turbulence in fluids, the turbulence that you're aware of if you've ever flown in an airplane. We don't really understand a lot of aspects of transport in fluids. And so it becomes relatively difficult to then also think about, a non-neutral fluid like a plasma, and think about how to measure the turbulence in that device. So in this device, the HSX, which is shown here, the plasma is kind of visualized in blue, and then we've got some external electromagnetic coils that are, in copper, and then also in this kind of tinnish color. And then there's this opening here called a box port. And so at this box port, we can install a whole slew of diagnostics. The diagnostics just measure some, particular parameter set, density, temperature, magnetic field, electrostatic potential, things like this. And so in this device, I have a particular diagnostic. It's a radiometer. It's a radiometer coupled with an antenna. So when you heat up a plasma to 20 million degrees, it's going to naturally radiate all kinds of light. One of those is called electron cyclotron emission. It's just a radiative process that is the result of that gyro motion that I showed earlier. By capturing that radiated, it happens to be in the microwave range. By capturing those microwaves with an antenna and then feeding that to the radiometer, we can get an extremely high resolution measurement of the electron temperature in the plasma. And by getting that measurement, we can kind of suss out the fluctuations that occur in the temperature, and those fluctuations are thought to be related back to the turbulence in the plasma. And so in terms of the research in this field, other than that specific diagnostic, usually you're making a measurement with extremely high resolution, very good digitizers, for example, of one of the fundamental plasma parameters, the density, the temperature, or the electrostatic potential. So yeah, I kind of think of new ways to arrange that diagnostic, think of new ways to incorporate, kind of better electronics with that for better measurements, as well as just kind of improving the software modeling, because it is difficult to kind of determine whether what you're measuring is, for example, from your apparatus, from the plasma, or from turbulence itself.
All right, thank you. Okay, so that we've just gone over outline of some of the current research topics and some of the challenges to overcome in making fusion technically possible. But what about the economics? So once we actually get it working, what markets are we facing or trying to target for the first on-grid fusion plant, Dionysi?
Yeah, so once we can do that, I think economics will still be a large factor there, right? The price of the power generated from a fusion plant, if that is not going to satisfy the market, it's not going to work, right? So there's a couple of people, some of them are from the Department of Energy, and then some of the friends, the fellows' names are, let me see here, Malcolm Hanley, Dan Slasinski, and a fellow named Scott Shue. They wrote this paper called Early Markets for Fusion, and they mentioned that it appears that fusion, when it gets to around $50 per megawatt hour, that's when it might be competitive with the existing kind of energies of today. Now, that's going to fluctuate, but they think that maybe in the US around $50 might be the price. But we can think of other markets like international game. I think Singapore and Japan, typically they have a very high cost of power and electricity. So over there, about $100 per megawatt hour, that might be more feasible. And those might actually be the first countries that utilize a fusion power plant, right? Not just a fusion device like we have all over the world, but the actual plant that's connected to a grid. Those might be some of the first places to use that. Now, you then also have to balance out this game, like, are we going to have carbon taxes, right? That will also change that game. So depending on how much people are having to pay for their tons of carbon CO2, that will maybe possibly make fusion a little more competitive in that market. But you also find that fusion is could not just be used for just electricity and that baseload power, but maybe other industrial applications. So some people have proposed for just strict heat generation, maybe for storing heat. You can also store the heat and put it into the grid at a time later on when the cost of power is more expensive. So maybe it's not just, on average, but at a time when energy is more expensive, that's when fusion can go onto the grid. People would be able to buy fusion power and make a deal there. Another one is, some of those kind of industrial applications. So electrolysis, the generation of hydrogen, those are some areas. People that just need high temperatures, that might be possible for fusion. So those are some of the areas there. Let's see, I have some notes, but I think that covers most of them. I don't know if anyone else has other ideas, chime in. Something glaring that I missed out.
I think a big question for a lot of people here might be, what are the timelines that we're expecting? Like, what is the current mainstream target for getting an actual power plant on the grid?
I don't want to answer that.
Dr. Ferry or Sarah, sorry.
Sarah, thank you. So the timeline that you're going to see for break even is around 2035 for most companies in terms of what they're stating. Once we came out and said 2035 for Spark, every other company came out and said 2034 for theirs. So by all means, they can have at it. So there is some level, right, of like you have to have aggressive targets to keep like your investors and the government and everybody on top of things. And and a common misconception is that this is something that is like misleading the investors. The investors in these companies tend to be very knowledgeable or have done a lot of due diligence into what the real risks are. They're comfortable losing large sums of money because of how their venture firms are structured. They know it's a long game. And that's also why, at least from the CFS end, a lot of the major partners are actually like major energy and oil companies. So for example, Eni in Italy, because these companies are comfortable with very long time horizons and they're interested in their, what they want their company to still exist in 100 years. And, if you look at the tea leaves, like we're really like looking at ways to get off of fossil fuel. So the oil companies aren't planning on just kind of disappearing. They'll eventually probably transition into other technologies as well. So that's a sort of an interesting factor there. The specific timelines are really hard to nail down. So you're going to hear 2035 for break even, but keep in mind that even if we are all successful in that, and I, very much hope we will be, I think that there's a lot of reasons to be very optimistic about the Spark technology in particular, based on how construction schedules are going and how the preliminary results that we had recently with the toroidal field model coil. But that is not a power plant, okay? That is a demonstration. It is effectively a souped up research reactor. It does not have a blanket. It does not have a tritium fuel cycle. It is not connected to the grid. It is not producing power. Those are all, for a long time, the fusion community has sort of dismissed those as like merely engineering problems that we will just be able to casually sort out once we have figured out the plasma physics. And they're rapidly learning that things like materials and engineering are, can be just as challenging in their own right. And so there's a big difference that, there's sometimes we don't know, like, is something impossible or have we just not devoted any resources to working on it yet? And it becomes, there's a lot of prioritization that goes on. Like, what do we need to put our resources behind to advance things quickly? We only have so much money in the field, especially on the research side. There's only so many people who are, working at an advanced level within fusion. Like, we are people resource limited more than anything else, honestly. Which is always why, like, the more students who get involved into the field, the better. So first power plant, ARC would be Commonwealth Fusion Systems version of a demo, of, ITER's demo. Other fusion companies have their own sort of succession of plans for, break even research plant to power plant. Targeting, I think, in publications, maybe they'll say around like 2040. It's hard to say, right? Like, there's also like a big difference between building a demonstration plant and building like a robust technology that you are able to replicate and have a market for and put it on the grid, right? We're all very aware of how things go on the fission side, and how things can easily get very slowed down and very expensive when regulatory bodies get involved. So there's a lot of groundwork being done across the fusion industry right now to make sure like the proper regulatory structure is in place. This is like, so the Fusion Industry Association sort of represents all of the fusion startups, and they're very on top of the policy aspects of this. So I think that, like, we may be like realistically, like hopefully 2050, but we're always trying to push that further. Like you have to be optimistic, but you have to be realistic too. And I think there is a lot of reason also to hope that if companies are able to reach that break-even status, for example, on a device like Spark or on some of the other devices that other startups are pursuing, at that point, the level of investment in these companies would become so high that we could start to maybe really accelerate the technologies at a much higher rate than what we're currently seeing. So you also need to kind of be wary of using current trajectories for research advancements and applying that to how things might look 5 or 10 years from now. So, yeah.
All right, thank you. I'd now like to open it up to any audience questions that you may have. And go ahead and type those in the chat if you want. Maybe while you're thinking those out, one more for Luquant. So we have several different approaches here on the call. We've said that. And have you ever thought of it as competition between these approaches, or is it more so a collaboration? What are your thoughts on that?
I don't know if I like that question. I mean, as a relatively young student in the field, I've always thought of it as a collaboration. I mean, there are, a lot of the underlying physics and challenges for example, I would consider Tokamaks and stellarators to be the front runners, at least for viable fusion plant. And as Sara mentioned earlier, I mean, Tokamaks are much more prevalent, but the number of man hours spent on stellarators is just far, far lower. So, I mean, I think there are definitely, thinking about private investment, for example, there's plenty of people that do seem to be relatively competitive and kind of strong-hearted about their magnetic confinement scheme of choice. But at the end of the day, I don't know how productive that kind of competition really is. Yeah, it definitely seems competitive, when kind of students are lining up and representing their own specific devices. But at the end of the day, I don't know how necessary that is. We're facing a lot of the same challenges in terms of publicity and in terms of physics and engineering. So,
all right, thank you. From Feng Lin, how dangerous will it be if an accident occurs in a fusion power plant? I think that's a good one for Sara.
Yeah, so ideally not very. It's still going to be a power plant. Any of these plants, especially when you have hot fluids involved, there's always like your first, from a probabilistic risk assessment standpoint, like the first thing that I'm thinking about usually is going to be like worker safety in the plant. And so a lot of those accidents might have nothing to do with like the radioactive accidents that we often worry about in nuclear. So that's just one thing to keep in mind. Like, this is still a very complex engineering. You have high pressures, high fields, high currents, like lots of things that you have to be very wary about from a safety standpoint. From a radioactivity standpoint, I think it is really important that when we're communicating about fusion power, We do not sell this as a radioactivity-free situation. I am a huge proponent of both fission and fusion power. And I think it's incorrect to frame fusion as sort of like an answer to fission, because I don't think fission is dangerous, first of all. But so usually we will contrast it against the presence of high-level waste. High-level waste that comes out of fission, the fuel rods in a fission reactor that are highly radioactive. And in the fission field, you never say high-level waste. You only call it spent nuclear fuel, because certain countries like France you can reprocess that fuel. There are different types of reactors that can continue to burn it. So even when it's dangerous, right, it still is potentially useful. But it is quite dangerous if you're not doing anything else with it. It needs to be sequestered from humans safely. And there are technologies to do this, but it's expensive. It's something that has to go through the regulatory process. It's something that people worry about. From the accident standpoint, there are the three major accidents that people know about. Those are 3 Mile Island, Chernobyl, and Fukushima. We're not going to, some other time we can get into the exact breakdowns of every one of those. But those were, again, fairly, I don't want to say low consequence, because that's really going to depend on how you're going to frame out the consequences. And so you got to be very specific about your language here. But that type of an accident where you have some sort of an explosion and a breach of your pressure containment, and then the highly radioactive fuel inside is exposed to the environment in a way that it spreads, right? So the high level waste, when it comes out of the reactor, is just in these solid fuel rods. They're not really going anywhere. So the danger is if something explodes and now you have contamination that can spread on the wind or in the weather, right? That type of thing is not something that we're going to ever have to contend with from a safety perspective when designing a fusion power plant. If something goes wrong with the plasma, it just kind of is going to go away. It just quenches itself. You have to sort of deal with that on other ends, but there's no situation where it explodes and sends radioactive material, that type of high level waste, into the atmosphere. What you do have to worry about, there's 2 main things to think about. One is the activation of structural materials from the very high energy, very high neutron flux. These are, we're looking at fluxes up to 10 to the 21 neutrons per second. That is 7 or 8 orders of magnitude higher than the highest flux fission reactors. So the activation can be quite serious. You have to really contend with this when you're picking your materials. And activation is when a material is exposed to neutrons, and it doesn't it doesn't fission, it doesn't split apart. But the material itself, when the neutron is absorbed into the nucleus, that nucleus becomes radioactive. So you can put a piece of steel into a high neutron flux, and then it can become very dangerous to handle that steel if it has been exposed to a certain amount of radiation. So for the vacuum vessel in particular, this is going to really, really matter, because some of the materials that would be the most obvious choices, like the Inconels that are corrosion resistant and very good high temperature, high strength materials, are so radioactive based on our analyses after being exposed to a fusion neutron spectrum for an extended period of time that from a handling perspective and from a safety perspective for the workers, I don't even know how we could contend with it. So this is going to be a major materials challenge to use lower activation materials like ceramics, I think, as we move forward and the field becomes more advanced. So again, that goes back to a worker issue. Public safety issue, this comes down to tritium. All of the regulations around the fusion power plants are going to come down to the tritium inventory on site. Tritium is really tricky to deal with. It is a low, on the whole, relatively lower consequences radiologically than being exposed to high level waste from a fission reactor. But the probability of a small amount of it being released, I think, is proportionally higher, because tritium is a much harder thing to contain. I'm not saying it's going to be leaking out tons of tritium, but thinking from an accident analysis standpoint where we try to eliminate every possible pathway of release, tritium is quite challenging to work with. It is very, very small. It kind of wants to go wherever hydrogen would normally go. So you have to have, lots of specialty materials, things called tritium permeation barriers, wherever you have tritium to keep it from exiting the plant. But again, we have a lot of avenues to contain this, but it is an engineering challenge that we haven't had the chance to practice at scale yet. So there is a relatively high probability of some small amount of tritium leakage that we have to contend with when designing the plant and try to eliminate that. And the danger, if a small amount of tritium is to be released, I don't really see it in general as a major radiological issue in terms of safety, but it is a major potential public relations issue if we are not honest with the public about what the potential radioactivity hazards are that are associated with fusion. Coming from someone, I've worked in fission for a very, very long time, and like, it is very, very hard to reestablish public trust if you lose it at the beginning. You don't get it back. So it's really important that we do this right and are like, we communicate what hazards are, what we know about them, how we're mitigating them, and, you move forward with like a level of transparency in order to build community support where we eventually site these power plants.
All right, thank you. From Jonathan Winters, are there EE undergraduate internship positions available to work on fusion research? I might be inclined to answer this one myself. I mean, I was in undergrad. I got introduced to it just by asking faculty. If you're at UW-Madison, you're very fortunate to be at one of the best fusion research universities in the country. There's just a lot of professors working on that sort of thing here. If you're somewhere else, it really depends on your location. Like, I would say look at your faculty at your particular institution and ask them what they're researching. Like, it might not be fusion exactly, but it could be something fusion adjacent as well. And as Sara mentioned, if you're the more people working on this sort of stuff, the better. Dionysi, would you want to add to that?
Yeah, again, if you're at UW-Madison, go ask any of us. The HSX lab is a big one. You have Pegasus, which is another big project. That's probably the Tokamak type. Kunal, I don't know, do you guys have a lot of undergrads? There's the Mirror project that Kunal works on, and then there's something called MST, Madison Spherical Torus. That's another program in the physics department that I think also has quite a few interns. So don't be afraid to ask. There's lots of projects here. It's not just physics undergrads here. Zander is electrical and computer. I think we have some engineering physics, some nuclear students. If you're electrical, there's plenty of work and help. So yeah, come on by.
I mean, generally speaking, yeah, there's definitely opportunities for, electrical, mechanical. Yeah, there's plenty of engineering opportunities.
You should maybe, if you're not familiar with SULI, SULI, as a research experience for undergrads that happens over the summer, and you get to choose between, I think, 3 candidates. Maybe Luquant, you can explain that better. But Princeton Plasma Physics Lab is kind of one big, highly requested lab that a lot of students try to work in. That gives you a lot of experience as well. So if you don't go to UW-Madison, that's another way to do it. I mean, heck, if you live near one of these fusion startups, you might even bother start asking them too. I don't see why not. Like we keep saying, we need a lot of help. So please hop on board. Would anyone be interested in seeing HSX? Do you want, Zander? I don't know.
You want to run upstairs and show it on your webcam?
I can, yeah, I can try to do that here. Let's see.
Yeah, sure. While he's doing that, Luquant, do you want to cover inertial confinement briefly?
Yeah, I can. So what was the question here? Status and prospects of inertial confinement. Yeah, so as many people on the call may know, I mean, inertial confinement has had kind of a relatively large breakthrough this year, achieving plasmas with extremely high stored energy and nearing ignition. So in particular, inertial confinement just is kind of the other confinement scheme that we didn't really mention on this call, but it involves ablating a deuterium-tritium laser pellet with a huge amount of laser energy kind of in place, and then trying to, I mean, you have that fuel pellet and then you bombard it, and then in principle you achieve fusion and then try to extract that. I don't, in terms of the status is that the National Ignition Facility has recently achieved a breakthrough. My understanding is that they haven't achieved such high performance since that day. And in terms of the prospects, I'm a little skeptical of this confinement scheme myself, just because I haven't heard of a viable way of extracting the energy from the fusion that you actually get. So specifically, yeah, you're going to ablate a pellet and release a huge amount of energy. But once you do that, you need another pellet, and then you need to ablate it again. So the frequency at which you have to ablate that and then extract the energy is a little silly. And I'm not necessarily, I'm not an engineer really. And so, thinking about it from that perspective, a lot of my plasma physics professors have kind of dismissed this. I mean, they are heavily biased toward toroidal magnetic confinement devices, but I'm not going to rule anything out either. One thing I might also add is that I think at least 60% of the research done at the National Ignition Facility is not actually fusion based, it's weapons development based. So that's just something to keep in mind.
Yeah, I think we had a speaker who was at the National Ignition Facility come talk to us about that milestone, and it's quite impressive what they've done. Now, to be able to power a plant with that, I think they said they needed to repeat that at 10 hertz with this very perfectly smooth little pellet. And if you see the pictures of what happens before and after, I mean, it's like they've had this very shiny little, it's almost like a teensy-weensy little gold thimble that contains that pellet. And afterwards, it has exploded. The little tweezer arms that hold on to it are just destroyed. So you would need to find a way to, one, have a lot of these pellets produced perfectly, very quickly, and in large quantity, and make sure you can reload those constantly. I think he made a joke that the energy released, which again was a huge milestone, is about as much energy as you'd get out of your Sunday morning donut. So maybe, but there's a lot of work to be done there. I guess if I'm still going after it, if you guys would like to see, that is HSX there. I don't know if you can hear me well. You can see that's the box port that Luquant has spoken about, the large coils. You can see a bit of the shiny stainless steel vessel behind all of that. And these very large support rings that hold on to it. Those are actually needed because the magnetic field gets really strong and it will actually stress and flex if those aren't there. So people might enjoy seeing that. This is about 2 meters from end to end. That kind of radius on average around 1 meter, I believe.
Yeah, about 1.3 major radius, 14 centimeter minor radius, something like that. Well, thank you for that little tour there. Somebody asked about the expected power for a fusion plant. No, you typed this answer in the chat already, Kunal, but for those not reading that, could you cover that again?
Yes, so the question was, what would the size of a fusion power plant be, that creates quote unquote a reasonable amount of energy? So again, this is something that depends on what flavor of magnetic or inertial confinement you use. For magnetic mirrors, if you were to make a 200 megawatt, power on the grid class plasma device, that would be about a 200 meter long, plasma. And then surrounding that would be a 200 plus, let's say 20 meters on each side vessel. And then surrounding that would be your, building infrastructure plus all the infrastructure you need to house all the, fuel handling, all your converting the heat to power systems and all the heating systems for the plasma itself. So you're thinking about, maybe if you think about it in terms of a box you put on the ground, maybe like 350 to 350 by 350 meter space to house a magnetic mirror fusion power plant device.
All right, thank you. From Tom Kaminsky asking about ARPA-E funding. Sara, you worked on an advisor to something like that, didn't you? Do you have any thoughts
Yeah,
on
I'm
that?
reading the question now. I worked on, I mean, I have two current ARPA-E projects. None of them are on this.
Oh, okay.
Let me see, realizing diagnostic evidence. Yeah, I don't have really any comments, any useful comments on this. I don't know if anyone else maybe could chime in.
Right.
Yeah, I think if I'm understanding it right, I think this question touches on what the inertial confinement versus magnetic confinement also kind of touches on, is that in the fusion community, the way you measure the quality or the performance of your device is through something called the loss in triple product, which is like the density of your plasma times the temperature of your plasma times the confinement time of your plasma. And you want to make this product of all three numbers as large as possible. And inertial confinement sort of trades confinement time for really, really high temperature and really, really high density. And if you can have a high enough rep rate, you can make up for that confinement time by just having this high value. Maybe for low energy nuclear reactions, it's trying to have a much lower temperature, but maybe have a much higher density and higher confinement time, and use that to create fusion power, which I don't know of any like experiment that is pursuing that in a large scale or mid scale experiment, but maybe I'm just not informed about the state of the art in that field.
Okay, thank you.
Be at least, if we can't answer that, it might be at least worth explaining what ARPA is for the rest of the audience if they're not familiar. Right, it's through the DOE, and they're trying to help. How would you say it, Sarah? Maybe less developed technologies, approaches, and ideas get development funding. That kind of higher risk things. Is that correct?
Yeah.
Is it to also go to market for some of them?
Yeah, so ARPA-E in general is tending to look at high risk, high reward situations. You can argue over what gets awarded and whether or not some of them truly fit that profile, but almost all ARPA-E projects are going to be looking at, there's a significant tech to market component in any grant application that you write, and it's a significant component of what they care about as you move forward with the grant. So ARPA-E is intended to accelerate research, but it is also intended to accelerate it onto the market or into some sort of thing where it is being implemented, whether that is through a government contract or something on the public market. That's usually the avenue. ARPA-E is not where you go for basic science research funding.
Cool, thank you. Another one for Kunal. What is I know you have several devices planned with the axisymmetric mirror geometry. Do you know which one will have a blanket, or which one in that? Yeah, like when are you planning on having power producing capabilities put into that?
So we're planning to make power, I think, is a question of how much funding do we get when. But to answer, I think the question, is the mirror, does the neutrons the same way? Yes. You can almost think of it as like the type of confinement you choose is independent of the type of reaction that's happening. And the neutronics of the system is dependent on the type of reaction that's happening. So if a magnetic mirror is doing your deuterium-tritium fuel cycle to create energy, it's going to have the same energy neutrons and the same neutron load on its vessel as a tokamak or accelerator would. The places where the neutrons get deposited might change because of the geometry of the vessel. But in general, you have to think the neutronics research on one type of device is applicable to every type of device, I would say.
All right, cool, thank you. Any other questions? If I'm going to take a second and put some further reading in the chat if you want to take a look at these sources.
People might enjoy seeing some of these plots of triple products, maybe. I can think of Sam Wurzel's paper. If you can see that there. This is kind of what Kunal had mentioned. You have that thing called the triple product. It's density, that's what that N is there. Confinement time, which is a little Greek T, tau. And you've got that temperature there. And so you can see that way up here, you have these colored bands, and that's what they're calling that break even there. And at some points I call what's burning plasma. When that gets greater than 1, that's when we're starting to see it producing useful fusion power, and that's when we're starting to think about maybe an actual economic power plant. So today we haven't made a device yet of these kind of typical ones, the Tokamak there or the Stellar, that have not achieved that break even. But what we talked about earlier was National Ignition Facility, that laser. That has a bit of a different kind of line there, and so they did get past that break even point. So that was there. That's a really impressive accomplishment on their behalf. I don't have this on apply as well, but people have largely said that this triple product has grown faster than Moore's law. So that's something people like to talk about, but I don't know if that really puts in context very well. I think these bands here showing how we're approaching the gain greater than 1 is what's important. That thing that Spark, that's what Sara has shown there. That's kind of the device she's working on. You see that's projected to be in this band where they're getting a great gain of around 10. And if you haven't heard of ITER, it's a very large international project. It's a big, giant honking machine in France, and that's also going to be done. They also expect it to be the gain greater than 10. I think maybe you can talk about it, Sara, but ITER is going to accomplish fusion power by being super huge, and Spark is going to do it by being super powerful magnets. Do you know much about the scaling on that, or?
Yeah, so the high temperature superconductors, like this newer technology, where we can achieve superconductivity using liquid nitrogen cooling instead of liquid helium cooling, so 77K versus 4K. It's still, you still need quite a lot of cryogenic equipment, but it's significantly more achievable or easier to work with than liquid helium is. It allows you to get higher power density in a much smaller package, a much smaller footprint. And in most of these cases, when you're looking at large facilities, a fission plant, a fusion plant, a lot of the cost scales pretty linearly or at least directly with the sheer size of the plant. So the high temperature superconductor technology, the REBCO technology specifically, is a big breakthrough for a lot of magnetic confinement concepts because it lets us do the same thing in a much smaller device. And then then also makes your engineering, when you go to make it into like a power plant with all the auxiliary systems, that's also going to be a little bit easier in theory. So that's sort of the basic difference is that ITER uses larger magnets to get the confinement.
I might add that also kind of ties back to the question earlier about the size of the actual power plant. There's just multiple kind of opinions in the field about compact power plants versus, and those kind of largely are using high temperature superconductors to actually achieve a smaller device. Whereas I guess I don't really know if people are still advocating for non-HTS designs, even in toroidal experiments, but those devices are necessarily larger because they just have smaller magnetic fields.
Yeah. And this is also kind of goes back to one of the major challenges of ITER, which for a long time was really the only thing in the game. ITER is a very old design that's taking a very, very long time to build, both because of its complexity and because it's not designed for simplicity or economics. It's a consortium of lots and lots of countries. And the worst possible way to build something quickly is to have every country design one of the parts and then they all come together, right? Like it's nice symbolically, but it's not how you would do something if you were building a commercial product. So the timescales associated with ITER are such that before ITER had even broken ground, right, it was already an out-of-date design. So ITER is like very important in a lot of ways, and we're going to learn hopefully like lots of important physics from it, but it is not representative of the technology that we expect to see eventual commercial fusion power. Like it's very different from what commercial fusion power would look like. No power plant is ever going to be built that looks like ITER, or frankly, I don't think that demo is going to ever be built either. At least not without significant changes that just take into account some of the advances that the field has made recently.
All right, well, if that's it for questions, I would like to say thank you very much, everyone, for joining us tonight. I know it's getting a bit late for some of us on the East Coast, so might as well end it here. All right, let's all thank our panelists for joining us tonight. And
Yeah, thank you, Zander. It's a really nice panel and nice to meet everybody and see the interest in fusion.
Yeah.
On behalf of IEEE, I'd just like to thank Zander for putting this together and giving us a very educational discussion.
Yeah, thank you for hosting us.
Hey, before we hang up, I think Mr. Jonathan Winters have another question. Maybe we can share emails or something like that. So, as soon as this chat closes, he doesn't feel like he's lost us forever.
Okay. Yeah, Kira, they'll send you my email and we can talk more about these topics if you want sometime later.
Yeah, put mine in there as well. So if anyone is curious, feel free. By the way, I showed you a tour through an annoying little webcam. It's probably super noisy. I mean, it will always be super noisy, but we love to host tours. So if IEEE wanted to get a bunch of people together, come on by. I mean, don't just show up unexpected, because I might be hiding underneath it with a vacuum pump hanging over my head. But by all means, if you want to do this again, I think we would be happy to do the tour. I think Kunal, I don't know if you guys can do tours, but at UW, I think it's pretty easy to see and tour stuff. I don't think Zander will be here by that time, unfortunately. Tomorrow he's running off to go be with Sara and MIT, unfortunately. But maybe you guys can do tours there if you're on the East Coast. So.
Mm-hmm. Yep, same thing here. We do tours. They need a fair amount of like just advance notice and legwork. But tours are they're definitely on the table depending on the research. Like right now, like a lot of times, like after TFMC, we've been remodding a lot of the different workspaces. So not everything is open right now or actually particularly interesting to look at. But also MIT also has a fission reactor, MITR2, and that is again also open to public tours as long as there is sufficient advance notice. And you have to schedule it and send passport information in because you go inside the reactor. But now that COVID precautions have been relaxed a little bit, that's starting to be on the table again. And it's a really cool educational opportunity. If there's a group of people who are on the East Coast, it's really fun.
Yeah, if you want to see the WAM facility, it's currently an experiment under construction. So if you come soon enough, then you'll be able to see an experiment under construction and something like intersect, running and operational as you move on to an upgrade. So that might be an interesting contrast as well.
You can also like shamelessly try to recruit while we're at it.
Yeah, everyone, if
I mean,
you're applying to grad school, please apply to grad school.
No, but for the working engineers too, right? Like,
also,
I'm
yeah,
sure...
CFS has lots and lots of job listings open for anyone who's looking to transplant to the East Coast. And that's true of a lot of the different fusion companies. Everyone's hiring, so.
There's a bunch in Seattle. There's the Fusion Industry Association.
Yep. Yeah, and then I put in US Energy or usfusionenergy.org. I think that the link that I put in the chat, Steffi and Arturo have done a really good job of creating a database of all available job postings from the internship level up to the senior career level that you can filter by like location and degree requirements and everything else like that. And the field is not, again, it's not open just to people who do like plasma physics. It's all of the engineering is needed.
Yeah, I mean, a lot of staff, I mean, we lost our, DC motor generator expert recently, so that needs to be filled. There's a lot of positions too for just staff scientists and people with engineering skills. Let me put the Fusion Industry Association too. You can see also these private companies now in the chat as well. So. Yeah, thanks for joining us. Super cool. Glad people are here.
Yeah, thank you. I'll do some research and check this out.
This has been a nice Midwest goodbye. All right. All right. Thank you again. You all have a good night.
Bye.